Hi everybody, I'm Miguel Morata. I'm a PhD student from University of Valencia. I'm inside the Flexinel project in Valencia. The header is Jochen Berrest. We are working in Flex investigation. Some of my colleagues are working in Flex retrieval from Tropomi at global scale, and also there are some colleagues working on time series they need to these traits. And in my case, I'm working on reconstruction of the full SIF spectral profile and its application to emulation. Photosynthesis is a critical process in vegetation, and it's important to know the photosynthesis products to understand the behavior of the vegetation. So this process releases solar-induced fluorescence as byproduct, and recently there are a lot of science studies about this product because it's very important to understand the behavior of the biophysical the vegetation and also to obtain predictions or make some analysis about the carbon respiration of the plants and all these processes. So the problem with this sun-induced fluorescent signal is that it poses very challenging because the detection of signal this signal is very weak in comparison with reflectance signal. And in main of the range spectrum, the SIF emission is blocked by other light reflections of the plant. However, there are narrow spectral absorption bands that in these bands, the sun-induced fluorescence has a higher value of the reflectance, and there are some methods that can retrieve this value at these narrow bands to obtain the SIF emission in these places. One of these methods is spectral fitting method that can retrieve it in the oxygen band A and B. And also there are a radiative transfer model is a computational tool used to simulate the behavior of the light in complex systems, for, such as the Earth atmosphere or the vegetation. In particular, SCOPE is a widely used RTM for simulating the radiative transfer in vegetation canopies. So in our study, we will use this RTM because we are focusing in sun-induced fluorescence spectra. Our study provides an alternative approach to reconstruct the full spectral SIF emission using principal component analysis. This principal component analysis is a dimensional T reduction technique that, as we use it in recent studies, can be used to reconstruct some spectra. The idea is to obtain an approach to reconstruct the full SIF emission from the oxygen A and B values obtained by spectral fitting method. After that, once we reconstruct the full SIF, we will use Prisma hyperspectral images to train an emulator and to obtain the full spectra of solar-induced fluorescence. As I mentioned before, we use the scope to obtain our lookup tables. Scope is widely used mainly in vegetation products, as it takes into account the interaction of solar radiation with leaves, the stems, and also the soil, as well as the fluorescence emission of vegetation. These RTM are based in physical properties and can simulate the behavior of the light throughout the leaves and the vegetation of the simulated models. The advantage of the scope is its ability to provide us with the full spectrum of SIG for its combination of input variables, spanning from 640 nanometers to 850 nanometers, so, with an spectral resolution of 1 nanometer. This means a total of 211 bands. So we created a lookup table of 10,000 spectra employing Latin hypercube sampling. We take a range of variables that are presented in this table, and we obtained the scope lookup table with all the spectra. We only save the spectra, not the variables, because we want to understand the shape of the spectra. We use principal component analysis to make the reconstruction. Principal component analysis is a linear dimensional T-reduction technique that is widely used to reduce the number of variables in a dataset. For instance, if the variables, or in our case, the dimensions, are highly correlated, we can reduce the dimensionality, keeping most of the original information. This means that, for instance, here in this graph, we have a two-dimension graph of many points. In this case, we have that all these two variables are highly correlated, and we can rotate the coordinate systems to obtain the V1 and V2. This is the principal components of the PCA. So when we rotate the coordinate system, we can obtain that the first principal components captures the most of the variance, while the other captures less the variance. For this reason, principal component analysis are also used to reduce the noise of the data, because sometimes this dispersion can be noise. So the objective of that is that when we apply the principal component analysis to our data set that has 211 dimensions, we can project the original spectra in the first principal components. As the variables are highly correlated, we will have some principal component or some direction coordinates that will not have so much variance, and we can project it to the first principal components, reducing the dimensionality and keeping most of the original information. And after apply the principal component analysis, we obtain a eigenvector matrix that we can use to make this projection to the PCA coordinates and also to return to the original coordinates. Also, I want to explain what is an emulator. Emulators are surrogate statistical models that are able to approximate complex processing at a fraction of the computational cost. So they are mainly used to surrogate RTMs, because RTMs are based in physical models and they process a lot of operation and a lot of iteration processes, and they obtain the variables. However, emulator can train with this data from RTM to obtain a statistical learning model based in the input-output relations. So emulators are very fast because they are only based in statistical models and can surrogate the original RTM, keep obtaining more or less the same information, but times faster than the RTM. So it's highly used in something like that. To understand more well what is emulator, for instance, sometimes we have a spectra from RTMs, and we use machine learning algorithms to obtain a regression to obtain the variables corresponding to the spectra. It's like the inversion model. However, the emulation has the opposite direction. The input of the emulation are the variables and obtain the spectra information. So they take the same that the RTM. The advantage of the emulation is that as regression is mainly used with a large dimensionality input to a one variable, the emulation has to achieve a link between many variables at the input and also a high dimensionality output. So the idea is that with these premises, we can use this advantage of this property of the emulation, that is the multi-input and multi-output, to obtain nonlinear relations between different spectra. In our case, will be the nonlinear relations between the spectra of radiance and also the spectra of sun-induced fluorescence. And also, to obtain this emulator, we use neural networks. So after the two parts of the study, where we develop a SIF reconstruction technique and apply it to high plant image, we will train an emulator using neural networks. Neural networks consist of interconnected neurons that are organized in layers. This is an example of a neural network with two hidden layers, and the neural network is trained with a large data set to and inside the age of the neurons we have the weights of the neurons. So with a large data set, the weights are changing until obtain a relation where the error is minimal to obtain the nonlinear relation between the input layer and the output layer. So the advantage of neural network are that they can train with a large data set. For instance, in comparison with GPR, the size of the model is proportional to the size of the data set. However, the size of the neural network will be always the same. So you can train a neural network with a large data set and you will have the same size of your neural network. While kernel methods, for instance, kernel ridge regression or Gaussian process regression, when you train it with a large data set, the model trained will be heavier and heavier proportionally to the size of the data set. And another advantage of the neural network in our case is that as we are using emulation, the emulation needs to have a high dimensionality at the input and also high dimensionality at the output. And neural network can achieve this easily, while other methods are mainly used for one output layer and maybe they are in a loop to obtain the other parameters of the output, and sometimes they are some computationally costly. So in previous studies, we have shown the high performance and accuracy of emulators to surrogate physical models. For instance, in a recent study, we used emulation to surrogate the spectral fitting method process to obtain the emulated SIF in the bands A and B. And we obtained an emulator that obtained very, very similar results, but at cost very low computational cost. To take an idea, the SFM takes some days to process an entire flight line from the place, and the emulator only takes few seconds to process the same entire tile. So finally, emulator can surrogate the SFM, but at very low computational cost. So with these premises, our goal is to emulate the synthetic full SIF spectra that we will obtain with our method from Prisma radiance spectra. So the data that we use it was based in a high plant campaign called HighFlex. The campaign was on west of Lleida, in northeast of Spain, and it covers a border area between irrigated and rain-fed semi-arid landscape. The image consists in 9 high-plan flight line lines, mosaiced in one image, and we split the image into subset, the train subset and the test subset. And also we used the two sensor, the Prisma sensor, we used the hyperspectral image as input for our emulation, and the high plan reconstructed full SIF as the output. And yeah, both images were acquired in 17th of July in 2021. And what we will use is from high plan, we will use the sun-induced fluorescence from SFM product with the values in the oxygen band A and oxygen band B with uncertainty. So basically, we will have only two bands, the emission values in A and B, and the corresponding uncertainties. This map has a resolution of 1.7 meters, and in the case of Prisma, we will use the radiance data with the 231 bands in the range of the 400 to 2500 nanometers with a spatial resolution of 30 meters. So we will sample two images to the spatial resolution of 30 nanometers. So we can take some pixels from the same place in both images. So after this introduction and all this data presentation, I will try to explain a bit the SIF reconstruction technique with this workflow. So First of all, we will create a scope dataset with 10,000 samples, 10,000 spectra, that will cover from 640 nanometers until 850 nanometers. So this is a total of 211 bands, and we will take the values in oxygen band A and the oxygen band B, and we will save it here. And after that, we will apply a principal component analysis to reduce the dimensionality to the two first principal components. So the two first principal components gives most of the original information of the full spectrum. And after that, we use it linear regression to obtain two linear functions that relates the oxygen band A and oxygen band B with the principal component 1 and the principal component 2. So basically, we will apply a linear regression to all these points from this data set to obtain the linear regression between the pieces as the dependent variables and A and B as the independent variables. So finally, we will have this linear transformation that we will have the values of pieces with these values that we will obtain with the linear regression. Once we obtain the linear transformation parameters, we applied it to the two bands SIF map. In our case, the high plant map. The high plant map has two bands, oxygen band A and B, the SIF emissions in here, and with uncertainties. These values are obtained by spectral fitting method, and we applied a linear transformation using the parameters that we obtained before with the scope dataset. So after use this linear transformation to the variables A and B, we obtained the principal components 1 and principal component 2. As this is only linear transformation, we can propagate the uncertainties from the beginning to the output. And after that, we applied a reconstruction with principal component analysis inversion to obtain from these two principal components the original dimensionality that we have at the beginning, the 211 bands. Sorry, there are mistakes, 211 bands. And as this also a matrix multiplication, because as I explained before, is a projection with the principal component analysis matrix, we can provide also the uncertainties from the beginning until the output. So we will have the full data cube of the original map, but with a range from 600 to 800 with 211 bands, and also another data cube with the uncertainties corresponding to this map. Now let's to explain a bit the uncertainty propagation. All these transformations are based in linear reconstructions. We can propagate it easily using the partial derivative method. So the first step where we obtain the linear transformation to obtain from the A and B values the principal component analysis. We can provide the uncertainties in A and B throughout the principal components, and we obtain it that the uncertainties of the principal components are this formula. So after that, when we apply the principal component analysis projection to project from the two principal components to the 200 dimensionality original dimensionality, we apply this projection, this formula. As this is also linear transformation, we can also provide the uncertainties from the principal components that we obtained before until the full SIF spectrum. And after applying this formula, we obtain it that the uncertainty of the 200 bands of the SIF are obtained by this formula. So all this process is also explained in a recent paper published. So if you are interested, there are more information there. And also now let's to talk about the results. So first of all, we evaluated the lookup table dataset, all the spectra, with a correlation matrix between the 211 bands, and we obtained this matrix. we obtained that most of the bands are highly correlated with the rest of the bands. And curiously, we obtained that the band A and V are highly correlated. The band V highly correlated with the first band, and the band A is highly correlated with the second part of the rest of the bands. So finally, with only these two bands, we have a very good correlation between the rest of the bands. So we applied a principal component analysis and we registered the cumulative variance, obtaining that only two principal components represents the 99.38 variance of the spectrum. So that means that most of the information of the full spectra are mainly contained in the two principal components, the two first principal components. We also evaluated the R square between the oxygen band A and oxygen band B, and we obtained a value of 0.26. This is good because we will use the values in A and B as independent variables. So we want to obtain a linear regression. So one of the premises that we need to obtain a linear regression is that our independent variables has to be really independent. In this case, this is our case. Our two bands variables are independent, so we can apply the regression. So we apply the linear regression to obtain the two transformation parameters, and this is the equations and the linear regression for the first three principal components. We obtain the statistics between the linear regression at the original values, and we obtain the prediction statistic in this table. You obtain it that the principal component 1 has an R square of 0.99, so it's a good linear regression, and the second with a 0.74 of R square. So it has also a good regression, but in the case of the principal component 3, we obtained a very low correlation, and this is because in this case the behavior of the spectrum are that they are not linear, and we are trying to regress a linear regression to something that is not linear. So basically, we obtain that this non-linear, we can't obtain these values with a linear regression. So finally, we use only the two principal components, because as we saw before, the two principal components gives most of the 99% of the information. After that, we obtained the two linear transformation, the two formulas of the planes, and we obtained these formulas. Okay. These are the linear transformation parameters as we saw in the workflow. This is A, B, and C are the slope A, the slope B, and the N. Okay, and we obtained it for the four principal components. We obtained it then that the two principal components, the relative error of the parameters are very low, lower than 1.992. But when we pass to the rest of the principal components, the relative error grows very much. So we can't use these principal components to reconstruct the full spectrum. So in our case, yeah, I did before the propagation of I explained the propagation of the uncertainties between throughout this linear transformation. And as in our case, the high plan map uncertainties represents around 10 and 20% of the values. So this means that the relative error of the parameters are so much lower than the independent variables. For this reason, when we derivated the formulas, we only derivated in the x and y, because the A and B has a very low error in comparison with the other parameters. So, and we applied these two principal components to obtain the full SIF reconstruction spectrum. And this is an example of this spectrum. The blue line is the scope original, and the orange line is the PCA reconstructed. As you can see, it perfectly matches to the original, and we obtained the root mean square error for all the spectra. And we obtained that root mean square error only reaches until 0.1, 0.15. that is very low values in comparison with the SIF spectrum. So we can conclude that we can reconstruct the original SIF spectrum with these linear techniques. And also, once we obtain these parameters to reconstruct the two linear transformation and the matrix for projection and principal component analysis, we applied it to an airborne sensor. In our case, a high plant image. It's important to know that the C values derived by high plant, in our case, were validated as in situ flux measurements in one of the fields here. The campaign obtained that in case of oxygen A band, the values are highly correlated and are near to the one-to-one line. But in the case of oxygen D, the regression is not so much close to the one-by-one line. So that means that the values of high plan that we obtained from this campaign needs to be calibrated. We can see that in these graphs where we represent 10,000 spectra of scope. We only take the SIF in A and B bands, and also 10,000 spectra from high plan with the A and B values. And we can see that when we don't calibrate it, the dispersion of the points are not matched with the scope dispersion. So when we apply the calibration, we obtain that all these points that are very dispersed here are in the same distribution as the scope distribution. So it's important to calibrate it because later, if not, we will obtain strange values because has not sense for the linear transformation. After the calibration, we implemented the technique that we developed, the full high plant image, and obtained a full SIF data cube from the original high plant image. As we explained it before in the workflow, we apply the linear transformation and the inverse principal component analysis, and we obtain finally the full map with a data cube with the full spectrum and also with the uncertainties. This is a graph of one of the pixels with the values of SIF and the corresponding uncertainties obtained by propagation of all these linear transformation. And also to compare the predicted values are inside the uncertainty provided, we evaluated the accuracy of the uncertainties. We rest the predicted values and the original values to obtain a histogram, and we obtained also the median of the uncertainties and the median. And we obtained that most of the values are inside the range of the median of uncertainties and the median. We also obtained the median and mean divided by 2 because in the case of oxygen 1D, it's true that there are some points outside, but in the case of oxygen 1A, practically all the points are inside the uncertainties. Every pixel has a different uncertainty, so we evaluated every pixel and we obtained that for all the image, 99.996% of the original values are inside the predicted range of the oxygen band A, and the 96.42% of the values are inside the range of oxygen B. So we can conclude that the uncertainty propagation works very well, and the predicted values are inside the range that we have with uncertainties. And once we obtain the full data cube for high plan, we evaluated we trained it an emulator to apply it to Prisma image. In this case, we trained an emulator using Prisma spectra as input and the synthetic full SIF spectra obtained from high plan as the output. So the two images, we taking some ticket for 40,000 points from the both images, and we train it with the spectra from Prisma as input and the full SIF obtained as output. We applied a dimensionality reduction because Prisma image has a total of 200 and something more more than 200 bands, and we applied a dimensionality reduction to obtain that 27 principal components represent 99% of the original information of the spectra from Prisma. So we used that to, in this case, we used principal component analysis only to reduce the dimensionality at input, and to reduce also the noise of the Prisma spectra. And we trained a neural network using 30 principal components at input for the reduced dimensionality of the Prisma, 5 principal components at output, because as we saw before, with only 2 principal components are enough to represent 99% of the variance of the spectrum, and 40,000 samples obtained randomly picking from the both images. We trained it with a five-fold cross validation, and we validated it with the subset test subset, and we obtained these statistics with an R square of 0.554 and a normalized rounding square error of 15%. And once the application of the emulator, we applied to the complete Prisma image, we finally obtained a full SIF spectrum for an image from space. And this simulator only take few minutes to generate the full SIF synthetic scene. So finally, we have a very large image with a full SIF synthetic spectra for each pixel. And also we sampled to flex spatial resolution to evaluate the heterogeneity of the crops, and we obtained these two images. So in future works, we will try to use simulator with uncertainties like GPR or neural network using dropout. We are thinking also to use nonlinear regression to obtain the relation between oxygen A and B and the principal components, because as we can see, the principal component 3 are not linear behavior, so we can use it also if we use nonlinear regression. Also, we can use the application of the SIF-Reconstructions to other high plane campaigns or other sensors that provide emissions from A and B products. This is because as our technique is only based in scope and principal component analysis, it is transportable to other places. And the SIF emulation can be applied to other spaceborne sensor like time or disease. We only have to train it with this sensor and we can obtain it. And the principal component reconstruction technique can be applied to future flex missions and derive additional SIF products like the max peak in fluorescence in A and B, or the integrated full fluorescence behind the curve. So in conclusion, we have a novel technique to reconstruct the full SIF spectral signatures from the retrieved values at oxygen band A and B. We reliable uncertainty propagation during all the processes to obtain the uncertainty for the full SIF emission spectra. And we have a powerful and reliable fast generation of full SIF spectra imaging, covering a large area for every sensor that provides oxygen band A and oxygen band B, and the emulation of the synthetic full SIF for spaceborne sensors. So many thanks for your attention, and if you have any question, you can ask me if you want. Thank you very much.